So this section is entitled Explaining Reaction Feasibility, and these are probably the hardest questions you get in the entropy topic. Generally because it's not using the delta G equals delta H minus T delta S calculation, it's more about analysing that equation to deduce whether a reaction is always going to be feasible, never going to be feasible, will only be feasible at some temperatures or below certain temperatures. So there's a little bit more kind of analytical work rather than just typing numbers into a calculator. Having said that, in this first question there's actually quite a lot of calculations to work out enthalpy and entropy changes, but you'll see the final part of it doesn't actually get you to calculate delta G, just by analysing that equation, as we'll see. So gunpowder gives you an equation for the explosion of gunpowder. So you've been given some delta H formation values for some of the things in that equation, and using Hess's law, calculate the enthalpy change for the explosion of gunpowder. So it does look like quite an intimidating Hess's law question, because there's a lot of things in it, but do bear in mind, obviously, that we've got 3 elements in this equation, and elements don't get anything in enthalpy of formation data, to kind of simplifies it a wee bit. So going from the elements that would make up those compounds, we've got potassium nitrate. We're given the value for it. It's going to be 2 times minus 493. Sulfur and carbon are both 0 because they're elements, as is nitrogen on the right side. Potassium sulfide has got just 1 mole of it, so it's minus 418. And then CO2 on the right hand side, 2 moles of it, 2 times minus 394. So to get from the right hand side to the left hand side to the right hand side, I need to flip the left hand side arrows on my cycle, so essentially just the potassium nitrate one, to get down, and then follow the arrows up to the other side. So what I've got there is going to be, well, if I do 2 times minus 493 first, it's minus 986. So flipping that for my Hess cycle manipulation, it's going to be plus 986. Then plus minus 418 for the potassium sulfide, and plus 2 times minus 394 for the CO2 values, should come out as a final value of minus 614 kilojoules per mole. In fact, I retract that. As you probably spotted, I made a mistake here. It should be 3 times minus 394, this is a 3 CO2. Putting that into your calculation will come out as minus 614 there. Apologies for that. Part D, you've been given a big table of data for this part of the question, and you'll be asked to work out the standard entropy change for the reaction. Again, it's a lot of calculator work, but it's not actually that difficult like a calculation to do, just kind of being careful with your calculator. So delta S equals the entropy of the products minus the entropy of the reactants. The products are CO2, N2 and K2S, just to make sure you're careful with your mole numbers. So we'll go for K2S first, so it's 115 plus N2 is 191 plus CO2, which is going to be 3 times 214 minus entropy of the reactants, KNO3 is times 2, so it's 2 times 172 plus sulfur, which is 32, plus 3 times carbon, which is 3 times 5.7. And essentially you can just chuck that all into your calculator in one go. It comes out as being plus 554.9 joules per Kelvin per mole. Now this is where the question gets a wee bit different. So in the previous question you might have, what we saw that you had to calculate delta G values using the delta G equals delta H minus T delta S equation. In this case we're not doing a calculation to finish with. All I've been asked is explain why this reaction is feasible at all temperatures. It's more like analysis work rather than calculation work. What we've just is this so far. We've worked out that delta H is negative and delta S is positive. And we have to work out how it feeds itself through the delta G equals delta H minus T delta S sum. There's a couple of ways of kind of expressing this, but probably the most sort of thorough way is to kind of go through like this. So if delta G or delta H is negative, delta S being positive means that T delta S will be positive, which means that minus T delta S, which is kind of the whole second half of the equation, is going to be negative as well. So essentially you're combining a negative thing and you're adding essentially another negative thing to it. That can only come out as negative no matter what the temperature is. Therefore, it's always going to be negative, so it's always going to be spontaneous. So delta G is always going to be negative because of that. So that's generally the way you lay it out. Express your delta H being positive and negative, and normally taught the minus T delta S term. Again, just because you want to combine the whole sort of second half of that sum into one kind of term with one sign there, which is negative. On to question 7, you're given the structure of citric acid, which is a carboxylic acid, but there's basically 3 units of it. Citric acid reacts with sodium hydrogen carbonate in an endothermic reaction. Blah, 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 blah. Part 1, write the equation for the reaction of citric acid with excess sodium hydrogen carbonate. Now that seems like a very horrible question. Think about it though, it's just an acid reacting with a hydrogen carbonate, and from GCSE you remember that an acid plus hydrogen carbonate goes to salt plus water plus carbon dioxide. They have given us a big space here rather than answered line, which does imply, if you see it, that you can just draw structures. So in other words, you don't have to try and convert this into one kind of single condensed structural formula. So it's fine for me just to draw out that structure. So CCH2 COOH, CCOOH and OH, and CH2 COOH. It's reacting with sodium hydrogen carbonate. It's going to make a salt plus carbon dioxide plus water. If you think about what's happening with the salt here, if it was just ethanoic acid, for example, we'd expect to make sodium ethanoate, which would be your H plus from your acid being replaced by the sodium. Just need to do it 3 times though, because you've got 3 acid groups. So essentially what you're going to do here is turn it into COONA in every position of the COOH group. All we need to do now is to kind of fix our balancing. We've had to use 3 sodiums to get our 3 salts, so I need 3 sodium hydrogen carbonates. That's going to make 3 CO2s and 3 H2Os to get that all balanced. State 1 observation that will indicate the reaction is complete. Simply just it's going to stop fizzing, or it's not going to get any colder because it's endothermic. That's pretty much it. Just you don't see anything happening with it at the end. Explain the meaning of the symbol delta S. Now, it's actually 2 marks here. So the delta S means entropy change. That should be what you're thinking of. That's actually only 1 mark. It's this wee symbol here, the wee plimsoll line, we call it. That means it must be a standard value. So in other words, everything's at standard states and everything's kind of 1 mole of everything. So standard entropy change for 2 marks there. Explain in terms of the expression delta G equals delta H minus T delta S why the reaction of citric acid proceeds spontaneously despite being endothermic. It's again, it's another one of those questions where there's no calculation, just analysis. So let's look at what we've got. They told us at the start of the reaction that is endothermic. Therefore, delta H must be positive. Delta S must be positive because you're making a gas, you're making CO2 in this reaction. So you've got positive delta H, positive delta S. The way we analyse it, as we said before, delta H kind of stays the same, but because we've got the minus T delta S term in this sum, minus T delta S is going to be negative. So for our reaction to be spontaneous, it has to be negative for delta G. So for delta G to be negative, what has to be true here is that the minus T delta S term has to end up being bigger than the delta H term. If this term is bigger, the negative is bigger than the positive and the overall thing will come out negative. However, if it's all the way around, if delta H is bigger than T delta S, the overall reaction will come out positive. So to kind of round off the answer, what you need to say is that the minus T delta S is going to be larger in value than delta H. You can use kind of like greater than, less than signs for that as well. But that pretty much answers the question. Question 8, ammonium nitrate decomposes in heating to form nitrogen 1 oxide and water. Write the equation for the decomposition. So just kind of breaking it down, ammonium nitrate, ammonium ion is NH4 plus, nitrate ion is NO3 minus. It's going to be NH4NO3. Decomposing to form nitrogen 1 oxide, so we have to be careful we pick the right nitrogen oxide because there's a few of them. Nitrogen 1 oxide's got a valency of 1, oxygen's always got a valency of 2, so swapping and dropping that gets me N2O. Then H2O is just H2O. Balancing, just need to plonk a little 2 in front of my H2O to get that balanced. Part 2. The reaction is exothermic and has a positive energy change, or positive entropy change. Explain why this process is spontaneous at all temperatures. So again, same kind of format before. Delta H is going to be negative. Delta S is going to be positive. If I put in my sum, delta G equals delta H minus T delta S, that reveals that the minus T delta S term is going to be negative. If delta H is negative and minus T delta S is negative, and I'm just pretty much adding these two terms together, the only kind of option is for delta G is always going to be negative. So just need to put delta G is always negative. Question 9 part A, explain the meaning of the term entropy. Entropy is the disorder, or the degree of disorder in a system. In a system just means like in a reaction you're studying, or kind of like a defined area, not like the universe. Explain why the endothermic reaction between ammonium carbonate and ethanoic acid is spontaneous. So it's kind of a contradiction of terms here. Remember, endothermic is generally unfavourable, but somehow it ends up being spontaneous and favourable to do. So we're not giving a lot to go off here, but basically you have to kind of read between the lines and look at this equation here. It's a carbonate reacting with an acid. That's going to make CO2, which is a gas. Any reaction in which you're making a gas from a solid and a solution is always going to have a very positive entropy value. So whilst delta H is positive, CO2 is produced, so the delta S value will be positive as well. That means that the minus T delta S term will be negative. And for the reaction to be spontaneous, what must be true is the T delta S term must end up being bigger than the delta H term, which means that your delta G value is going to be negative and therefore spontaneous. In part C, explain whether reactions which have negative entropy changes and positive entropy values are feasible or not. So let's analyse that. Negative entropy changes means delta S is negative, and positive entropy changes means delta H is positive. The effect of delta S being negative means that T delta S is going to be positive. Or sorry, minus T delta S is going to be positive. If delta G equals delta H minus T delta S, what we basically got there is a positive term where we're adding another positive term to it. That can only ever come out being positive for delta G. So delta G is always positive. And that means that the reaction is never favourable because you can't get it becoming negative with any temperature. Last little question in this section, question 10. The entropy formation of CiCl is minus 178, while CiCl2 is minus 796. Calculate the enthalpy change for that reaction. It's another kind of sneaky Hess's law question, so we're going from elements, because this is formation data. So CiCl is going to be 2 times minus 178. CiCl2, 1 mole of it is minus 9 or 796. Ci is just an element itself, so just 0. Need to flip this out to go from left hand side to right hand side. So we get 2 times plus 178 minus 796 will give me my enthalpy change. Comes out with a value of minus 440 kilojoules per mole. Explain why the term T delta S may be neglected when predicting the feasibility of the reaction shown in C part 4. So it's not actually asking us to predict anything, just why T delta S might be neglected. So why could we leave out the delta S term if we're looking at this equation? Basically, if you look at the equation they've given us, it's a solid going to solid plus a solid. Hopefully remember that solids tend to have quite low entropy values. And if you're just changing solids into other solids, whilst the entropy will change a little bit, it's not going to be a drastic change. Like it might be only plus or minus 10 joules per Kelvin per mole, which is quite minimal. Basically because everything is a solid, so all species in a reaction are solid. you can say that the entropy change will be very small. And if it's very small, you can sometimes just pretend it's not there at all.